Hello everyone, how are you? How's everything? I hope everything is going well with you. If you remember, in the previous session we talked about the rectifiers and we told you about the rectifier circuits and how we use the bridge circuit or the other method with two secondary on the transformer to create a rectifier. But many of you asked me later on that this part that I explained is just for the diode rectifier part. So what about the filter? What does this part do? And why do we always see capacitors in the rectifier circuits? So I'm going to answer this question quickly for you. Look, as you remember, we either used this combination, this method, with two secondaries, or the bridge diode to create a full wave rectifier. It means we we could convert this sinusoidal signal into this blue signal that you see over here, that it's always above the x-axis. But now you remember that we said that we want an actual DC. It's not enough that everything just is on the positive side, but it's still sinusoidal shape. We want something flat. This is where we need a capacitor. How? Look at this circuit. Look, when I make a simple circuit like this, one power supply here, one diode, and one capacitor. So imagine that this black sinusoidal wave is my Vin, okay? So when I turn on this power supply, whenever I'm in the positive side, the diode will conduct, it's on, and it passes the voltage, right? It passes the current. So the same voltage will be at the both sides of this capacitor. So it will start to charge the capacitor. So the capacitor, when the voltage is increasing, the capacitor is being charged until this point where the voltage starts to drop. So the voltage in the power supply starts to drop, but this capacitor is already full with this voltage. So it keeps its voltage. Until this voltage drop, and then goes to the negative zone. Then this diode even turns off. But the capacitor is charged with the voltage, this V out, this blue, and it's gonna stay at this voltage. So this composition would be ideal, right? We just charge this capacitor and boom, it's giving us a great, beautiful, direct current. But there's one problem. The reason that we can see that this beautiful straight line is there is that there is no load here. But we want to connect this rectifier to something. There is going to be a load that's going to use this voltage, right? So the moment that we have a load, then this capacitor will be discharged. So this shape will be the more realistic shape. So when the capacitor is fully charged, then this resistor here wants to absorb this power, this voltage which is here. So that's why after the peak, when this thing is full, when the voltage starts to go down here, our load here, which is R, is going to use the voltage, is going to use the power which is stored in the capacitor. So that's why the level of the voltage will start to drop, because this resistor is eating it up, right? It starts to drop, and within this time that is dropping, my power supply is also having its own cycle. So it's go down, it goes to the negative, then it comes back to the positive. Then when it reaches to the point that it's more than the current voltage of the capacitor, which is here, then it charges the capacitor again to the maximum. And then it starts to go do its own sinusoidal cycle, but the capacitor starts to discharge again. But if you look at the pattern of the blue signal, you see that this is much more acceptable than the sinusoidal shape that I had before. It's almost a line with some ripples, these ripples that you see over here. So what can I do to make sure that these ripples are as close as possible to a straight line? Because look, if this R was eating up the power faster, this ripple could have come down all the way here. So I would have had like a very bad shape, like it would have had like another periodic shape with a lot of ups and downs. But as long as the ripples are short, it's not a big deal. So what should I do? Look, the combination of that R and C are creating a kind of a filter shape for us, right? So to keep the output from decreasing too much during capacitor discharge, we must select the value for C and R so that the time constant RC is much greater than the discharge interval, because there's actually time involved here. So we choose the R. If we choose the R and C correctly, we will manage to have a very reasonable ripples. The time constant is found by CR. So as long as we make sure that CR is much greater than T, which is the period of the sinusoidal wave, we're gonna be fine. So this is the reason that we are using capacitors, or as you wanna call it, a band pass filter, basically in this low pass filter here. But as far as we concern, this combination of R and C here is to make the signal as close as possible to the direct current or to DC. Another application of the diodes that you need to know, and it's very important, is the limiter circuits. What are the limiter circuits? Limiter circuits are the circuits like this, that they can cut your output at a certain level, at limit, positive limit and a negative limit. For example, if you had an increasing like straight line, like a ramp line like this, we can limit it at L plus or L minus with the help of a diode. Or let me show you another example like this one. Imagine you have a sinusoidal shape, but you do not want, your circuit cannot accept the voltages more than a certain level. So you can create a limiter to have this blue output from your circuit with the help of diodes. How? This is how we are creating limiter circuits. Let's look at the first circuit, this one. In this circuit, look, in all of these circuits, we're going to imagine that our input is going from minus infinity to plus infinity, something like this. So imagine we're going to have a straight input that starts from minus infinity and goes to the plus infinity. So we're gonna see how would our output look like. So if this red line is our input, we want to see how the output looks like. So I erase the input so we can look at the output. First, take a look at the circuit. Look, this is our V in, that, as I said, starts from minus infinity and goes to plus infinity. There is a resistor R, and there is a simple diode with the drop of voltage of 0.7, and here is the output. So let's see what will happen when my voltage is negative in this region. Okay, here we have a negative voltage, so this diode is off, is turned off, right? So whatever we have here goes right to the output. So the output and the input look exactly alike. Let me remind you of the input. You can look, the input looked like this. This is your input, this red line. So you see the red and the blue in this region are exactly matching each other. But when Vin starts to become 0.7 and more, what will happen? Then this diode starts to conduct. It's gonna turn on. So it looks like a wire. It's like a wire. So it's gonna be a short circuit here, right? So no current will go this way. Everything will go this way, right? So everything that was coming from here, right? It will go down here, right? And goes back all the way there. So nothing will go to the output. So the output will show the drop of voltage on two sides of the diode, which is 0.7. So you see the output will stay like this. So let me remind you again, your input was this, right? Your output, when you were in the negative cycle, because the diode was off, your input was going exactly to the output. So it was exactly matching. The moment that we were exceeding 0.7, the diode was on, so the current was going like this. So the output was a constant 0.7, because then we are reading the two sides of the diode. So this was how we limited the voltage in circuit A. Now let's look at circuit B. This is pretty similar to the other one, just the direction of the diode is upside down, right? So in this case, when V is in the positive side, the diode is off, right? Because the direction of the current is here, is this way. It's coming from up to the bottom, so it's gonna be off. So whatever is in the output will be shown at the output. Again, I'm gonna remind you the input again. Our input is always like this, okay? This is our input. So in the positive side, since the diode is off, it's going to be matching this. But the moment we go to the negative side, it means that the direction of the current here, here will be positive, right? Here will be negative. So it means the direction of the current will be this way. So then the diode, the moment that here is 0.7 more than here, it means we have to be at voltage minus 0.7. Here, the diode will turn on. So the direction will be like this. Then it gets here, so of course it goes this way, right? It's like a short circuit for it. And then exits this way. So nothing will go here. So V out only reads the two terminals of the diode, which is minus 0.7 in this case. So you see, this is a limiter voltage that limited our output this way. Once again, how did our input look like? Our input was this, right? It was something from minus infinity to infinity. So this circuit was allowing all the positive ones, but not allowing the negative sides. So try to look at the other circuits as well, C, D, E, and try to explain for yourself that how did it work. For example, C is the combination of A and B. So you use one diode this way on one diode, the other way around. So this is how you have limited it both at plus 0.7 and at minus 0.7, where your output was still looking the way that it wanted to go from minus, and look, the input was still like this, right? It goes from minus infinity to infinity, but the output looked like this. So this is one example. So try to explain the D and the E for yourselves as well, and if you couldn't make sense of it, come back to me with your questions. This is a very interesting topic. So I hope that you all enjoyed this session as well, and have fun. I'm waiting for your questions and comments. Take care. Have a nice day. Bye bye.